Every day, the Earth as we know it is bombarded by cosmic rays. We don't really know where they come from, but they're made up of a variety of different subatomic particles. One of these particles is the muon. These little guys are produced at the start of the troposphere and have a lifetime of about 2.2 microseconds on average, after which they decay into electrons. But this poses a problem. Muons travel very close to the speed of light, and assuming that they're produced 12 kilometers above the Earth's surface, that would take them 40 microseconds to reach us. Yet, they only last 2.2 microseconds on average, which means that only a very small percentage of very high energy muons would be able to reach the surface before they decay. 1.91 times 10 to the power of negative 6% of them, to be exact. This doesn't really add up, because actual measurements show that we have about 1 muon coming in every minute per squared centimeter. So, what's going on? Well, the answer is a spectacularly beautiful piece of evidence for special relativity. Since muons travel very close to the speed of light, all sorts of strange things begin to happen. Because the faster something moves through space, the slower it moves through time. Essentially what's happening is that the muon's internal clock is ticking slower than ours, and so it's able to move much further in 2.2 microseconds than in our system of time. This is known as time dilation. And what about from the muon's perspective? Well, to them, it's actually the Earth and its surrounding atmosphere that's moving towards them. And as it does, it's stretched orthogonally towards them. The distance they now have to travel is much smaller. These two phenomena, time dilation and length contractions, are fundamental to the way the universe works, because they account for why the speed of light is constant everywhere, and why nothing can ever go faster than it. The factor by which time and space is warped in a system is known as the gamma factor, and it depends on the speed at which a body is moving. In this case, the gamma factor is 11.2. So the dilated lifetime of the muon is now actually 24.6 microseconds, and the contracted length is only a kilometer, which takes only 3.3 microseconds for the muon to traverse, more than enough time for it to reach the Earth's surface. When you take into account these two phenomena, the percentage of the number of muons that can reach us is raised to about 22%, much bigger than before. So the next time you're looking for a solution, try considering the problem from every perspective possible.